All motors.
Thank you. So I'd like to thank the organizers for the kind invitation to speak to you all. So I want to tell you a story about sort of shape control, but not in the way that we've heard so far in this workshop. We've heard a lot of really, really beautiful things about how you can get complex shapes out of the inherent, material properties of the system or the phase properties of the system, things like that. I want to tell you about a more design-oriented way of perhaps looking at things that's made possible by nematic solids, which we've heard a tiny bit about, but not very much. So let me kind of move ahead. And I should say that most of this work actually was sort of begun in my time here at Cambridge with Mark Warner, who I want to thank at the beginning, and then I'll thank again. But he was integral to all of this and had a hand in all of it. So the idea, when you want to, out in the real world, when people want to build something, particularly something complicated, you need to plan what you're going to do. You need to have a blueprint for it. You need to call in a bunch of workers. You need to requisition a bunch of materials to put things together. And eventually, after you have your plan, you can do lots and lots of work on that plan, and then you can build a beautiful thing, right? And so with the advent of sort of active materials, this sort of, pie-in-the-sky idea sort of propelling this is it possible to take your blueprint, to take a blueprint that you've planned, and just have the blueprint, the actual sheet of material that you've blueprinted, turn into a thing, right? And then possibly even switch it back and forth to some, sort of motor system or some sort of active system that you can run with. So obviously this is going to require some kind of not typical material. And so nematic solids is the material of choice for this system. The idea is that a nematic solid is you have these polymer systems that have pneumatic mesogens on the side chains or possibly on the main chains, and the sort of random walk statistics of the polymer change from, typically they're spherical, but when you move into the pneumatic phase, the random walk aligns preferentially along the direction of the director field, and you can get length changes that are coupled to the strength of the order parameter. So this is the basic idea in the microscopic sense of what's going on. And you can activate, of course, any way that you can change the order parameter, either through temperature or chemicals or even light, depending on what the mesogens are. You can get this order parameter-driven change in shape. All right, so I don't want to spend too much time on that. I want to advertise quickly that there is a way to activate these things with light instead of temperature, which would be nice for device design. During the Friday session that we're sharing with iCamp, I'm going to say a little bit more about this, as is Mark. So I just want to quickly advertise that. But the basic idea really is that you have these, you can either dope with or actually use as the mesogens molecules like azobenzene that change their conformation from something that is rod-like to something that is very much not rod-like when it absorbs a photon. So you can control the order parameter that way. Okay, so there's two main classes of these nematic solids. There's the elastomers, which are very, very rubbery. They're the kind of the first ones that were studied. You can get extraordinary strains, 300, 350% on this plot, even higher in some cases more recently. So they're very, very soft, much like rubbers are. And they also have this very, very fascinating coupling between the director and the imposed elasticity that's referred to as the soft mode, where an external loading on the system can, if you imagine you have the director, you have a bulk piece of the material, and you have the director, so the long direction of the random walks of the polymers all end up like this, and you pull it like this in this direction, in the normal direction, the directors can all tip over for free in some sense. And so you can get a strain response with no energy cost. So this is referred to as the soft mode, and it's very interesting and very subtle, but for the purposes of design, if you wanted to write some pattern that would become a thing, it's not at all what you want. You want to be confident that the director field that you have written is the director field that you are working with going forward. So luckily, the other class of nematic solids, the nematic glasses, solves this problem. So it's essentially a polymer glass where you just greatly increase the density of the crosslinks in the system. And so the director becomes immobile because of the much constrained motion of the polymer paths. You can only hit relatively low strains. So in this plot by work done by Brewer and his lab, they're kind of cycling back and forth at 2% strain. You can hit up to around 5% strain in the glasses. So you lose in degrees of deformation, but you gain in the ability to write things and be sure that what you've written is still there.
Carl?
Yes?
The strains that are getting larger, they correspond to some moduli going to zero. Which one is it? Is it young modulus, bulk modulus?
Which,
those large strains respond to some...
yeah, this is the Young's modulus. It's under load. It's a linear strip under load. It's the Young's modulus. Well, I mean, they're more and more loaded, but yeah, yeah. It's the, I mean, you have that soft mode. Yeah, I mean, you have zero modulus up to some point. Okay. So one of the things that, is this visible or should I turn off the light? Do people see this? Okay. One of the simplest things you can think, and we've heard a lot about topological defects so far. So one of the simplest things you can think of patterning with is a simple topological defect, right? You can imagine that you have some variance in the field that's well controlled, it's symmetric. It's sort of an easy first guess for something to look at that might give you something interesting. And so, you know, I don't want to belabor this because we have heard a lot about topological defects, but these are both +1s. In general, you can write a Franck energy minimizing defect in this form, this nice simple form as a function of the space angle. And for the +1 case, you can locally rotate the directors to get different versions of the same thing. So these are both +1s, but the geometry of the +1 is different. Okay, so what happens? So let's start on the left with the azimuthal case. And let's imagine that we're going to heat the director, heat the system, so that so you're heating the system. The order parameter is being lowered, so the system wants to shrink along the direction of the director field, and it wants to extend by some spontaneous Poisson ratio in the normal directions. And so if you look at an integral curve that lies tangent to the director field, it's the perimeter of some circle in a +1, and you get some deformation, lambda, which will be less than 1 for a heated system. So the perimeter wants to shrink. At the same time, remember I said by the Poisson ratio, you will get the opposite sense normal to the directors, so you get an extension of the radius. If you turn the directors around into the radial case, you get the opposite senses. You get a expanding perimeter and a shrinking radius. And notice, of course, that this is all completely symmetric, so I could have taken any circle in the material. At all length scales, it's the same thing. All right, well, what you've done here effectively by changing the perimeter and the radius is change what the value of pi is in the system, if you like. You know that by the theorem of Bertrand-Ducoupe-Tissot that there is no Gaussian curvature, you know, anywhere in the limiting sense, but you might have a singular limit, and in fact you must, because the Gauss-Bonnet theorem guarantees that you have some Gaussian curvature in there, since the normal curvature around the curves varies from the flat case. And I say flat case because there is Gaussian curvature. And you can see relatively simply that in the original, the first guy on the left, the case with the azimuthal heating and azimuthal texture, you must get something that looks like a cone. A cone has the same relationship between a shrunken perimeter and an increased radius, and you can relate the opening angle of the cone directly to the imposed strain. I should say from this point, well, modulo what I'm about to say after I say this, but from this point forward, I'm going to be assuming a thin sheet, right? We're interested in the deformations of a thin film where you can work with multiply charged defects, where you don't have to worry about the bending energy, where you only have to worry about stretch. Yeah, so unless, and I will retract that assumption at various points throughout the talk, but I'll point that out when I'm doing it. One of those points is right now, which is, of course, at the very tip of a true cone, where the Gaussian curvature actually sits, the bending energy diverges. So if you had any real thickness at all, you can't have a true cone because of the energetics. And you can work out that Gaussian curvature becomes smeared out over the tip as a result of the bending energy, and you get a small spherical cap of order of the thickness of the material. Interestingly, in the limit of low strains, that spherical cap becomes large, and you get a metastable region where the whole sample prefers to pay the strain cost of staying flat, and then it pops up. And this has been seen recently in simulation by Robin Selinger and her group, which is interesting and nice. Okay, so what about the other case where you had a radial texture? So here the perimeters are getting longer and the radii are getting shorter, and so you must have some system with negative Gaussian curvature concentrated at a point. Mathematicians would just call this a cone again, but as a physicist, it felt like we should say something slightly different because we don't think of these crumpled shapes as cones. So we call them anticones. You effectively get a modulation in the azimuth, but the generators of the shape are all straight lines. So if I were standing in the middle of the thing, the shape would just be up and then down and up and then back to where I started, with some number of nodes along the way. Because of that generation by the straight lines, you do get, in fact, that the Gaussian curvature everywhere off of the defected point in the center is 0. So you might imagine using these things at a first pass as cutting strips that contain the defect, and using these things at a first pass as kind of sort of interesting takes on cantilever actuation, right? Instead of just a pure bending mode, you could have something that sort of flips in like this or twists. You can imagine using this for different, more complicated actuation. Okay. So I've shown you a way that you can get a conical corner piece, right? So there's still a lot to do. We still want to eventually get to the ability to make multiple corners. But it would be nice to have smooth shapes too. And this is going to be a quick advertisement for the Friday talk, because I'll talk more about it then. But the answer is yes, we can make smooth shapes. If you allow the strength of the order parameter to change as a function of where you are on the sheet, you can get surfaces of revolution directly out. And I want to skip through this because I'm going to talk about it. If you want to see that, come on Friday. Friday morning, I think, is when I'm scheduled. Okay, so we talked about plus ones. So as you know, there are lots of other defect charges in two-dimensional nematics. Halves are very common, but the others you can get as well. Can we leverage the other charges? In particular, if you really want to make lots of corners in a sheet, you don't want to have to put plus ones everywhere because then the boundary condition will be very complicated, a very, very high charge boundary condition. You would prefer to be able to pattern with sort of the defects of your choice. All right, so to move forward, it's necessary to restrict oneself a bit, right? You could say, let's just throw down an arbitrary director field. Let's just, put in any old defect with any kind of modulation, some kind of smoothness, some kind of fluctuations, but that's too complicated. So we're going to restrict ourselves to a small set of what I'm going to call a language. It's going to have a vocabulary and a grammar that you can build with, and you can understand completely what these pieces do when you put them together. So we're going to start with the vocabulary. You can have there's 6 pieces to the vocabulary I'm going to propose here. You can have a wedge cut out of a plus 1. You can have a triangle with, and so again, from here on in the talk, I should point out, I'm not going to draw the little dashed lines for the director everywhere. I'm just going to draw integral curves because it's easier and perhaps easier to understand for more complicated textures. So you can have a wedge with this join down the middle with a restriction on the join that I'll talk about in a second. Or you can have a triangular wedge with the director just parallel to the base of the triangle. In addition to these three, you can have the versions where you've rotated the director locally by pi on 2. So you can have a circular wedge of the radial +1 defect, just like this. You can have a triangle with a join down the middle where the apexes of the meeting at the join points towards the base instead of the tip. And you can have a sort of a straight triangle like this where the director is normal to the base of the triangle instead of parallel to the base of the triangle. So these are the 6 pieces we're going to work with. For each individual piece, you can imagine just having that piece, an isolated triangle of material, of pneumatic glass, like this, and like this, just sitting, on a lab table. And you can imagine heating it or straining it. And you can see very quickly what's going to happen is that the lateral extent will change somehow, and the opening angle of the cone will change somehow. And you can calculate what the new angles are as a function of the imposed strain. All right. So now I told you that that's the vocabulary. To get a full language, you need some rules for putting it together, so you need grammar. So there's nowhere I can squeeze in a rule about an Oxford comma, so I won't. But in particular, when you stitch these things together, there's 2 ways you can do it. You can either stitch them together in such a way that the pneumatic director is just continuous across the join. So you can imagine putting this wedge onto this wedge, and then you have a smooth director field and nothing changes. Or you can imagine joining them in such a way that the angle of the director meets the join, is the same on both sides, right? And you need this because you get the length change of the projected normal direction and along the director direction at the boundary, and that length change must match, or else you get a macroscopic buildup of different lengths across the discontinuous boundary, and the material will tear itself apart, or at least be very, very stressed. Okay. So I kind of started this section saying, what about other defect charges? So let's put some of these wedges together to make other defect charges. So here's a -1/2, right, where I've taken 3 of the wedges that had a join down the middle. Here's a +1/2, where I took just a full half of a regular +1 and a full half of a nothing. Here's another way of writing down a +1/2, where I've taken 2 of the wedges with a join down the middle and 1 nothing. And you can calculate, so remember we had all those simple equations for the change in the angular opening. Once these wedges have been put together, there's no longer an angle to open, right? You've got a continuous piece of space, of flat space there. And if you add up all the angle changes, you get a total angular deficit or surplus. And in 2 dimensions, it's a happy coincidence that the angular deficit or the angular surplus is identically equal to the Gaussian curvature charge at a point. So this gives you a direct way, and a very easy way, of calculating the development of Gaussian curvature at each of these points. It is an isolated point of Gaussian curvature, and so it must be conical again, conical or anticonical. I don't want to take too long on this, but because of the fact that you have discontinuous jumps, there is a subtle ambiguity in whether or not you call this is this really a +1/2? When you imagine moving the director field through one of the discontinuities, you could say that, oh, it rotated by this way or it rotated that way to get there. And depending on how you do that, you might assign some different charge. That's fine, just as long as you're consistent with the choice of the direction of rotation across a discontinuous boundary, it doesn't end up mattering. And ultimately, what you call these charges doesn't really matter either. I mean, it's just a matter of whether or not you can stitch the things together and get curvature that you can control. It was somewhat surprising to realize that there is a way to do this without a defect. This doesn't map onto a defect at all. It's just sort of a bend softening. So you have a harsh bend across. If you move down in this direction, you have a harsh bend across this boundary, and then you cut that bend up into 2 softer bends in the 2D direction across this boundary. And this carries a Gaussian curvature charge. It's smaller. You get an interplay between positive and negative pieces, but it's there. So that is another thing that, that's not defect related that you could imagine patterning. Okay, so I showed you that you could stitch together these things around a point to get different charges with different defect charges that correspond to different amounts of Gaussian curvature upon activation. Can you start actually tiling these together in the plane to get more complicated structures, which is sort of the goal. At least, if you could do it simply, it would be nice. So now, again, I want to, for the second time now, I want to take a step back and reintroduce a small thickness to the sheet. So one might think, if you imagine this texture with concentric squares, at first pass you might think that it just makes a square pyramid by the symmetries. However, because of the role of bending, bending is a convex function, the bending energy, and it would much prefer to be spread out instead of along these folds coming out of the pyramid. And so in any system where you have a bending cost, this texture just gives a regular old smooth cone, right? With a different amount of Gaussian curvature at the tip than you would have thought if it were a circular, it were sets of concentric circles, but a smooth cone nonetheless. So that's one place where the bending enters. The bending can do things for you, though, which is nice. So you imagine, so here, this is the first example of something that you have lots of things that you've patterned. So here's an array. It's got 9 plus 1 disclinations in the square sense, and it's got, I guess it's got 4 minus 1s and then 8 half minus 1s and 4 quarter minus 1s. You can imagine tiling with it. And so now in this case, when you strain this, you remember in the isolated case you get the smooth cone. When you strain this, though, if you imagine the smooth cones coming up next to one another along the line of intersection, you'll get a much more complicated curve. You'll get a curve that runs up and down like this, where the cones are coming in and coming out. And that curve carries Gaussian curvature. And so you get Gaussian curvature distributed along lines if you allow this system to smooth out into a smooth cone, and that incurs a costly stretch penalty. And so that stretch, because we're in the thin sheet limit, even if you do have a small thickness, that stretch wins out over the desire to spread out that bend, and you do get folds here. So you actually get an array of pyramids. Now you can pop the pyramids up or down, and if they pop in the same direction, you get a fold between them. But if they pop one's up and one's down, there's no fold. And so the bending energy gives you an antiferromagnetic Ising model on this kind of sort of elastic system, which is cute, but I'm not entirely sure how much is useful. But it gives you an egg crate. Okay, another example of something you can pattern, again with the pyramidal shape. And this is basically just leveraging some extra defects that you don't really care what they're doing to concentrate the bending, right? So you have these extra defects. They nucleate this little moat sort of texture around the pyramid. And because of the need to concentrate that Gaussian curvature at the new points, you can no longer really spread out the bend energy. And so you get a proper cone, a sort of a quasi-isolated proper cone. You can imagine doing things a little fancier. So if you take a texture like this, where you have 4 joined triangular defects, this is going to make a cube. So you imagine, the way to imagine this, how this works, is you say, there we go. So you say that this defect in the center becomes this corner of the cube. And then this region, from this defect to this defect, and laterally from this boundary to this boundary, becomes this face of the cube. And likewise, the top bit becomes the top face, this becomes this face. And so, and the other guys fold up around the back. So the cube sort of, it's almost like a claw. The cube closes together, and on across the cubic diagonal from this is a vertex that's not in the material. It's the meeting point of the 3 prongs of the original triangle. And so you certainly could imagine applications for something like this. So more curvature effects. I mentioned a moment ago that when you had two cones meeting one another, they gave you some line of distributed Gaussian curvature. If you actually want to have that, you can seed that in. And it's very simple. You just write down two different +1s. You let them meet at some line. And you look at the line, and you see that a restriction of the angles meeting, the directors meeting at the same angle, is satisfied, but now there's a spatial variation to the angle of meeting. And that gives rise to this sort of mountain pass geometry, to use the language of Randy's wonderful talk from Monday. So these textures were sort of inspired by conversations with Randy and his group at the time that they were doing that work. And much like that talk, you can get the whole class of two-dimensional focal conics, in air quotes. And they give you the same. I think Randy even showed a picture very much like this on Monday. Whereas instead of an abstract space, this would actually be a real material making two mountains of different heights. I'm not sure how to boost this system in real time. You'd have to boost it, while you're writing it. Okay, another thing that comes up all the time in nematic textures is grain boundaries. So you can imagine writing down just a plus or minus 1/2 grain boundary that connects a director going this way to a director going that way across some length scale. So this one, if you strain it a little bit, the Gaussian curvature on the positive side kind of makes this little series of ridges. You get crumpling, right? Because ultimately you want elongation along here and contraction along here. And so the only way, the way for the system to do it to first order is just to crumple the part that wants to get longer, and the part that wants to get shorter can just stay flat. And the presence of the curvature defects actually gives you exactly the right polygonal corners in exactly the right places to make this happen. As you increase the strain, however, and again, the bending energy, of course, now there's another place where the bending energy enters. As you increase the strain, because of the magnitude of the folds is much lower, you can get a curved geometry out of this, where you have two sort of cylindrical sections that are joined to one another. You can imagine, this is harder to imagine for design, but this is kind of nicer, I think, to think about from the theory side, because there are a lot of open questions here. But you can imagine seating these things onto shells instead of flat sheets. And there are some sort of relationships to design in a moment. So if you put the director onto a nematic solid cylinder, such that the director is along the axis, nothing funny happens, that just flexes. But if you try to tilt it at all, you get out of register once you move completely around. The length change, because of the periodic boundary condition, once you've moved around the cylinder, you find that the shear directions have completely displaced you relative to where you needed to be hooked up. And you get a large buildup of stress as soon as you tip it at all. And this is totally topological, because completely anywhere local, you can satisfy the strains completely. And despite that, you still get large stress builds up. Stress builds up because of the winding mode of the cylinder. You can wind the cylinder back onto itself and make a torus, and here now the situation suddenly is reversed. For the typical smooth torus, there is no stress-free configuration, again, because of the topology. But if you allow yourself to hide some of the Gaussian curvature of the torus onto lines, so you make this shape where it's sort of a big thick cylinder with a thin cylinder cut out of the middle, and you imagine just the surface of that thing as your torus that you texture. Now there's another completely stress-free solution to this. So this, I just want to point out that this happens, but a deeper understanding of this is still elusive. But I think it's interesting, and I think there's a lot going on there. You can, go to other shell shapes, spheres. So you pattern two antipodal +1s. You, of course, have to get, as has been pointed out, you have to get a total charge of 2 on a sphere because of the Hairy-Ball theorem. You strain this, and you get sort of an elongated rugby or American football type shape. These come up in some of the microfluidic work of Rudolf Zentel. I think he calls them cigar shapes. I'm not entirely sure it's exactly the same, but I think it's very similar. I think this is the effect. I'll skip that. If you imagine straining the opposite sense of the spherical shapes, where you have to get an anticone on the top, you can see you're going to have a problem. The spherical belt of the system has one topology, but the anticone, which wants to fluctuate up and down, has, there's no way to link that together in a smooth way. So you're going to get stress across some top region. The polar regions will be stressed somehow. And when you smear out, and I think this actually makes a sort of nice connection to Luca's talk, when you smear out that negative Gaussian curvature at the tip, you get a capping mode that's something like a pseudosphere or a pseudospherical cone that connects the kind of bulged sphere to the negative parts at the top. And this looks like sort of like a pumpkin. And I think I believe pumpkin was the word that Rudolf Zentel uses for the microfluidic droplets. Okay, another thing that you can think about patterning that might be useful is if you can have a surface that you start with some topology that has some holes in it, and then you want to flex the holes or do something active with the holes. So the reason why you might even think this is possible in the first place is going back to the very simplest thing that I started with. You take a azimuthal +1 disk and you cut a radius out of it, and then you heat it. That radius just opens up, the thing stays in plane. The radius opens up and you get sort of a Pac-Man shape. And if you cool it, that radius, it buckles out of plane enough to slide over itself, and you get a sort of an envelope closing. So if you can put in these things in such a way that they kind of work in concert, you can get a controllable sort of pore on a very, very small length scale in principle. So this is the sort of pattern you want to use, at least in the simplest case. So you get opening around these plus defects that kind of bracket the ends of the strip, of the cut, and you get retraction of these defects that sit at the middle of the cut. And so in the flex case, it opens up into a diamond. And you can calculate the exterior angles of all of the polygons in the system, and they all obey Euclidean geometry, and so there's no out-of-plane motion at all. It's just a completely flat pore that you can control with the heat or the light. They also tile, so you can make an array of them. And these have been seen in an experiment recently by Dick Brewer and his group. So this is a real effect. Okay, so now I want to return back to the point I made about restricting ourselves to this vocabulary and grammar for writing and building things. And I want to say a few words that are a bit more speculative about smoothly varying textures. So there's some things that I can say for sure, and some things that I can not say for sure, but we'll say anyway. So you all know what a smoothly varying texture looks like. Let's skip that. I already gave you the simple equation for the director field of a defect in the one constant approximation. So things to point out about this. R does not appear here. This is scale-free, right? This is completely scale-free. You can zoom in or zoom out. It looks exactly the same. And so you would hope that any surface that arises from this must also be scale-free, at least in the limit that the bending, in the true flat limit where the bending doesn't enter into it, the surface must be scale-free as well. You have this curious property that if you locally rotate the director, so if you go everywhere in space and rotate the director by the same amount, so along this line here, let's say you want to move it up by this much, and then you go here, so there we move like this, so here we move like this. So you do a local rotation at every point in space. So for these textures, that local rotation is equivalent to a global rotation of the entire system scaled by the defect charge. And so in particular, I mean, it's a nice symmetry, but in particular, because of the fact that rotating the director in our system by pi on 2 interchanges the strain roles of heating and cooling, that means that this correspondence gives you, for all the defects other than m equals 1, where notice that this fails because the denominators blow up, gives you a correspondence between rotating the actual surface you create and heating and cooling. So this is very much not the case what happens with the +1 defects, right? You cannot rotate a cone, you know, a solid body rotation of a cone to get an anticone. But by these symmetries, that must be what you can do for the other, for the smooth cases of the other defect charges. Okay, so you can actually, you can get partway there by just writing down the deformation gradient tensor and relating it, you know, directly to the metric in the surface. And you can turn the crank on differential geometry, and you can work out a formula in the reference frame of the material for the Gaussian curvature of the final deformed surface for these defect charges. So notice this is going to be a very strange surface because it diverges at the origin, but as you move to the origin from different angles, the sign of the curvature divergence changes. So you come in from one direction, it's diverging positive. You come in from some other direction, it's diverging negative. So this is sort of hard to wrap your head around what these might look like. So one family with all the restrictions and symmetries, you can pin it down to a sort of broad family of surfaces that you grow from logarithmic spirals. So the logarithmic spiral, of course, is a scale-free curve. And if you develop a surface around a log-free spiral such that the cross-section grows in a scale-free way as well, you can get a log-free horn, a cornucopia, a horn of plenty, a ram's horn. These occur in nature. And these are the families of surfaces that hit the right symmetries and obey the right restrictions. But it's large enough that it's difficult to write down specific answers. There has been some nice recent experimental work done in Timothy White's group of looking at some of these. So maybe there's some hints here. So this is lots of different Frank minimizing disclination defects. Perfect. These are thin, again, very thin films, but they're sitting on O-rings, so you get this external radial stress that, and also a very specific boundary condition. So this is very recent, and so I just wanted to kind of throw this up here. It's in press, but it's a nice result. Of course, most of these, let me go back to the, oops, too far. Most of the log horn type surfaces would not be able to sit and register with an O-ring type boundary condition. So there's going to be some interplay between that boundary condition and this family of pure surfaces that we expect to see. There is one solution. Let's look at the +2. If you look at the +2, you can imagine building one of these surfaces. So we'll look at just the half plane of the +2 first because it's easier to see what's going on. So the half plane of the +2 has integral curves of the director sitting in a sort of clamshell configuration. So you can imagine if you heat the system, individual circles in the clamshell, you can just rescale to satisfy that length change. And now you must increase the length between the circles as you move out. And so you can work out how much you need to increase that length by tipping them out of plane. And you discover that the surface you get satisfies the symmetries. It's this sort of self-interpenetrating logarithmic horn. And if you promote it to the full +2, you get a pair of these log horns that sort of eat each other as they move around. And this is not self-intersecting anywhere, even though it looks complicated, it is complicated. But there's no self-intersections. This is completely allowed, again, without bending energy. Clearly, the complicated things that are going on in the middle, the bending cost would be divergent. So you would get some cutoff close to the very central Gaussian curvature defect. So just to say another quick word about the structure, which is sort of a relationship, maybe some speculative relationship to smectics, but there is, you get this sort of, they're certainly not equidistant layers, but you get this sort of layered effect. And down the z-axis is a helicoid, something that is very close to, actually a pair of helicoids that are interpenetrating as they move down. A helicoid with a variant pitch. As you move close to the origin, the pitch gets faster and faster. Again, that's just an observation. And so again, I want to thank Mark. And I also want to thank Kaushik for some help on the theory. And then our experimental colleagues, Dick Brewer, Carlos Sanchez-Samolinos, Lawrence DeHaan, Timothy White, and Michael McConney. And thank you all for your attention.
Thank you very much. Questions?
Hi, Carl. I really like this last picture, if you could put it back.
Yeah.
It's quite intricate. Maybe you can up.
The half version or the whole one?
No, the full one. Let's do the main, the full catastrophe.
Yeah.
So if I want to put a cutoff on the bending energy,
Yes.
if I treat the picture on the left as a nematic Frank free energy director, and I put a cutoff on the logarithmic divergence of that, how would that, give a core radius to the defect? How does that translate?
Right. So
is that the way to do it?
I think so. There's another interesting symmetry between the defects that I did not mention, which is that defects of charge. You can take one of these sort of curved boundaries with the Seclets of Dupin style thing. If you take a circular one of those and you put that circle over a defect, then the only other charge that you can put in there to match the boundary conditions is a charge of if you start with charge m, it's charge 2 minus m is the one that's congruent. And so in particular for the +2, that's charge 0. So you can take if the bending energy becomes too bad, my guess is that the system would take there's some small capping region where the director will act like it's just straight. And if you then deform that into a surface, when the sides kind of spiral in, you see they're all sort of planar, right? You take circles of the same radius on both sides are like planes that are rotating like this. And so when you move that into the center, you can just cut it off with a plane, right? It's kind of a little circular disk of a plane that kills the rest of the log spiral.
I was intrigued by the pumpkin structure. Do you have golf balls too? Dimples?
Yeah, lots of dimples. That's a good question. So the trouble with dimples is it would require lots of other positive defects as well. So you would get both, in such a case, you would get both dimples and little mountains. So you get a little thorny ball. But yes, I don't see why not. You certainly could pattern that, and that should be what you get, absolutely.
Time for one more quick question.